Our next speaker is Boris Sofman. Boris is an engineering director leading trucking at Waymo. Boris leads a team that builds on Waymo's technical foundations and experience to pursue the tremendous opportunities in trucking. Prior to Waymo, Boris was the co-founder and CEO of Anki, where he and the team sought to bring technologies from robotics and AI into mass-market consumer products. Anki developed various entertainment products and shipped over 3.5 million robots and devices around the world. Previously, he also worked on off-road autonomous vehicles and ways to leverage machine learning approaches to improve navigational capabilities in real time. Boris holds a bachelor's degree in computer science and a master's and PhD in robotics from Carnegie Mellon University. And now, over to Boris.
Hi, I'm Boris Sofman. I lead autonomous trucking at Waymo. And I'm going to speak today about some of the unique challenges that autonomous trucking brings to the broader AV challenge. And in particular, given the focus of scale, it might be especially interesting to learn about some of the unique data challenges and labeling challenges that are at the core of really solving some of the long tail of autonomous driving on trucks. So a little bit about Waymo. At Waymo, we are building the Waymo driver. So the driver is meant to be, in some ways, the operating system for many autonomous vehicles. It's used for cars, for trucks, and over time, many platforms. And so this is a technology that really powers all of the vehicles and applications we work on in order to make them safe, efficient, and capable. You're probably familiar, especially in San Francisco, with the Waymo cars, the Jaguars. They're equipped with our 5th generation autonomy system. We've been operating in Phoenix since 2020 in fully autonomous operation. And now we're operating fully autonomously in San Francisco and 2 parts of Phoenix and expanding very rapidly. And so this is a technology that's already starting to scale. We're servicing customers and employees and continuing to develop our capabilities and breadth and starting to really begin our scale and commercialization. Waymo Via is the newer application at Waymo. It started in 2017. And the idea for Waymo Via was to extend on the foundational technologies that powered Waymo cars and the ride-hailing application in order to enable trucks to be fully automated. So we're working on Class 8 trucks, 53-foot trailers, and really working on the transportation of goods. So this is the logistics and goods parallel of people transportation on the other side of Waymo. And in a lot of ways, we're able to actually leverage the foundation within the company in order to accelerate the path towards autonomous trucking and then really invest our resources in the challenges that make trucking a distinct challenge from the vehicle side. And oftentimes we actually see that value flow back and forth between the two applications. So why trucking? It's a pretty incredible application, both in terms of safety and business viability and need. As you know, overall, there are 1.3 million deaths annually. Over 4,000 people die in large truck crashes in the US. That's about 1/10 of all automotive crashes. When they do happen, accidents do happen, they're incredibly much more serious and can be very tragic. And there's a giant shortage of truck drivers. That's 80,000 today. It's going to grow to over 150,000 over the next few years. And the utilization is actually quite poor, less than 50%, with 1/3 of trucks driving completely empty miles. Because there's so many constraints about where the trucks are available, where the drivers are, what their shift times are. And all of this leads to a $1 trillion industry in the United States that's actually straining in terms of both capacity and utilization. So there's a tremendous opportunity here to help on all these fronts. In order to do this, just like on the car side, you have to build an L4 platform that is fully redundant. This means that it has the ability to have backup steering, braking, actuation, power supply, and be able to withstand any type of failure, which at scale is going to happen when you're driving huge amounts of miles. And so we've been in a partnership for many years with Daimler Trucks to build the first L4 capable trucking platform. We actually are now testing them in autonomy mode on public roads in Dallas and Phoenix. So it's quite exciting. And so these trucks are pretty amazing because they're based on the existing platform, but they have to be redesigned in a lot of ways to really make all of these systems truly capable of handing off in a safe way, and then fully integrating with the self-driving system of the sensors and the computers that actually run the Waymo driver. Under the hood, a lot of really amazing work that goes into these redundancies, the communication systems, the power supply, data. And all of this is not integrated on top of a final truck. This is actually redesigning one of their existing platforms, the Cascadia platform, and really doing this in the beginning to where it is capable of being mass produced with the Waymo driver into an L4 capable truck. And so once you have the platform, a lot of the deepest investment, as you can imagine, happens in the Waymo driver, the actual systems that enable the autonomy to operate at a level of quality that allows us to actually launch fully driverlessly. This is something that is, to a largest degree, we can share between the cars and the trucks. There's a feedback loop where the learnings from one feedback and improve the other platform. We focus very much on making sure that the core technology stack stays consistent, the infrastructure is aligned, the eval framework is aligned, and we're reusing as much of these building blocks as possible on the way to actually shipping an autonomous system. However, trucking introduces some really unique challenges. So on the ride-hailing side, a lot of your operation is in dense urban environments. You're driving 20, 30 miles an hour. With a truck, you're focusing your operation on 65 mile an hour driving on a freeway. You have a large and articulated trailer. This thing is massive. It's 53 feet. You have to merge into dense traffic. You have to really think about that positioning at all times. It causes interesting occlusions in your sensor field of view as you turn. The vehicle dynamics are incredibly limited. When a truck is fully loaded, it could be 80,000 pounds. That means its acceleration and deceleration are quite different. So all these challenges mean you have perception, planning, motion control challenges are quite distinct, as well as obviously the safety framework and the validation. We'll focus today on the perception side, where because of the vehicle dynamic challenges, you have to push for much longer perception range, deal with those occlusions, think about unique long-tail cases that occur on these many-hour routes. And all of that forces you to really address the data and the systems that drive your learnings in a very unique fashion. This starts with the sensor suite. So the sensor suite for the trucks at Waymo are leveraging a lot of the same building blocks and sensor components as we use on the Jaguars, but they are in a different permutation and in different quantities, and there's some unique sensors as well. You'll see, first of all, there's two pods on either side that deals with the, they're flush with the trailer, so you don't get occluded if you were to have, like you would if you were to have one main pod in the middle. You have combinations of LiDAR, cameras, radar. There's different types that are meant for near range and long range. And in particular, there's this brow of cameras up front that has various permutations of very long range focused cameras that becomes a foundation of the long range perception system on freeways, in combination with the radars that also have quite long range. And so these end up complementing each other quite deeply. One of the biggest advancements was this generation of LiDAR. Again, it's used on both the car and the truck. The previous generation was very capable and was a very impressive sensor. This was the fourth generation self-driving system in LiDAR. The fifth generation is a gigantic step up. This is a view of what the LiDAR sees, and it looks like a camera image because of just the sheer density and range of this LiDAR. But this is the type of data that we are now receiving back in our cars and our trucks. You see that circle here is where the vehicle is, and you can see the richness of the data that comes back. And so the trucks have two of these. It's incredible, and it's the foundation of a lot of the a lot of our perception systems, where this type of three-dimensional understanding of the world around you is fairly unparalleled as a backbone of a lot of the system that you use. At the same time, as we mentioned, LiDAR ends up having very long range, but you do end up being able to extend it much further when you use high-resolution cameras. So our cameras are able to get data out, see things at a kilometer and beyond. This becomes incredibly useful, where that reaction time ends up being a key part of what a truck needs to navigate. Radars, again, redesigned for a freeway use case, are able to cut through weather conditions, rain, fog, in a really successful fashion. They complement cameras with very unique types of data and uncertainty models at range. Hugely valuable, different type of signals that needs to be labeled in different ways. And so here's a really interesting example where we're driving and we react to a vehicle stopped on a shoulder at over half a kilometer in this particular case, and move over far, far, far ahead of time, where you see that coming up on the bottom image there. And it's actually a really good thing that we're able to do this, because especially in dense traffic, it can be difficult. And here, there's actually a pedestrian that's changing a tire or mucking around in their door, whatever they're doing it on the driver's side facing the freeway. That's a pretty scary situation. And even though we've changed away for safety at a really long distance, we then start to really detect the pedestrian when we get closer, and you avoid being exposed to the really dangerous, rare situations by being able to react this far out. And it's and this is something that we're really leaning to the strengths of all the sensors in order to do these sort of things, particularly at night. Quite exciting. And so this drives a really interesting discussion around data and how we utilize it and really think about understanding the long tail on a freeway. So data challenges. So you obviously have rarity of data. That long tail examples happen infrequently. There's an even more challenging sparsity of events on a freeway. You have weather conditions, fouling of the sensors, and you have even a fundamental challenge of how do you label at a really long range where the ground truth is kind of uncertain, just by nature of the type of sensing you're doing. And so most of our exposure ends up falling into the typical driving case, and what we really try to optimize for is these rare, strange situations, which becomes a mix of techniques that lean into both supervised learning as well as some really interesting kind of tricks that we've picked up on that allow us to try to shortcut some of these challenges and really both develop and validate the system in a more effective fashion. And this becomes useful because you got some really weird stuff that happens on a freeway. Here, a grill is falling out the back of a pickup truck at 65 miles an hour right in front of us. This is actually during one of our recent runs. You have a dog walker who walks daily on I-45 between Dallas and Houston. So this is how you can tell if somebody's really serious about trucking, particularly if they're operating in Dallas. If they don't know who the dog walker is, they're not serious about trucking yet. Everybody who's driving that stretch, they've seen the dog walker, and so that he's a staple of I-45 on that stretch in the mornings. Construction workers walking around carrying signs. You have giant cut-ins and pullovers and bizarre behavior of vehicles in front of you. You have giant houses in the lane, animals, vehicle fires, all sorts of interesting situations. You have construction zones that by definition, you're going to have a sparsity of examples that you have to deal with, where there's a huge amount of almost infinite permutations you can have in construction zones, and they're hard to discover. They're genuinely rarer and more complex scenarios that are oftentimes more one-off that lead to really challenging circumstances. And so when you think about the long tail and thinking about how to tackle the data problem, construction zones is right at the core of it. And so one of the ways that we've started to really think about how to approach this is on top of the more traditional supervised learning techniques, we think about synthetic data, where we compose scenarios and objects in real scenes in order to help us really create a broader diversity of situations that we might need to handle. And so there you can then start to really think about primitives like cones and signs and other aspects, which you can collect a lot of data for, but the way that they're composed in a scene and the semantics that represents ends up being really a powerful opportunity to lean into synthetic scenarios and and compositions. And so that's quite interesting. And so now we can actually train these models and really think about both real and synthetic primitives, but then really starting to kind of tune our system so that even at really, really long range, we're able to detect these objects, even if we might not have seen nearly as many situations in real life to to feel comfortable about training in a purely traditional fashion. We can even do synthetic compositions, as I mentioned, of the full scene, create these scenarios, and really kind of test the system and stress test it to minor changes, and still have this be consistent and in a realistic simulation of what happens in the real world because of the abstraction of these primitives. Shoulder blockages, and so all of these are scenarios that, on top of real world driving and the sort of rates that you're able to learn about your performance, you can really stress test some of these areas of your capability space in a way that builds confidence and exposes you to things you wouldn't have otherwise. Weather is another really interesting situation. So we have huge amounts of data. We drive tens of millions of miles. We simulate tens of billions of miles. But weather is, in some sense, another lens on every one of those miles. And you can't just recollect all that data with arbitrary weather conditions. And so we aggressively lean into data augmentation and simulation for weather as well. So in this case, this is a scenario where we've simulated kind of fog and smog. We do a lot of the same things with rain, weather and fouling, where we collect a lot of data, but then are able to learn models for sensor degradation so that we can simulate that on any arbitrary example and up-level the amount of training data that we have to work with. That ends up being incredibly powerful. Fouling has the same shape. So this is carnage from a drive from Dallas to Houston. There are a lot of mosquitoes on that drive, and this is what your sensors look like after that drive. And so this is the kind of stuff that's on your sensor pods. And so there are cleaning systems on all of our sensors, but there are periods of fouling and then the wipers themselves that end up obscuring portions of your field of view. And so this really helps us think about sensor degradation, reliability, resilience to these sort of challenges. Filtering challenges and multi-sensor modalities in both fog and heavy rain. On the heavy rain case here, this is all of the random noise and signals from our sensors are being filtered out in real time as we're driving in rain. So there's a lot of challenges that happens, particularly with LiDAR and camera, that end up being very sensitive to weather conditions. And so putting it all together, this is actually quite exciting, where what you're going to see here is a collage of our simulation approaches, where you'll see the first couple of seconds of the scene that is the real scene that we drove in, and absolutely everything else after that is actually augmented and simulated. And this becomes a really foundational capability for stress testing our system in the full permutations of the domains that we need to operate within. So let's see, let me play this. Here we go. This is the real scene, and then everything else is permutations of the types of experiments that we would throw at the vehicle that simulate nighttime weather conditions, different environments, different sensor conditions, and all of this is something that we can very aggressively iterate on in simulation and really detect when we might potentially be catching the boundaries of our capability suite, and have to be able to kind of adapt or develop in a different way. So here, all types of intentionally thrown in kind of augmentations of vehicles, pedestrians, cones. Same thing applies to weather conditions, wet roads. And so all of these are incredibly valuable kind of validation techniques that can help us improve our confidence in the conditions that we drive, and become also very good regression prevention tests, given the realism that we're now able to simulate on both the sensor level and the scene level, which is quite exciting. So another related example, so we talked about long range long-range detection, classification. This obviously becomes very useful for understanding the flow of traffic, the semantics of what's going on, lane closures far ahead of time, so that if you can give yourself 10 extra seconds to react and merge out of it, you can prevent yourself from being caught in a very difficult situation. So the question becomes, how do you actually evaluate these really long-range examples where you have a vehicle very far away out, the better part of a kilometer, and you need a ground truth. And not just in the classification that, yes, this is a vehicle, but in some sense, one of the most important elements is localization, where you care a lot about whether it's in your lane, in another lane, or on a shoulder. As you can imagine, the way you react to each of those could be vastly different based on the circumstances. And this is where a lot of our facilitation that we've developed to facilitate labeling at really long range and turn it into a problem that we're more familiar with actually comes from pairing up our self-driving trucks and vehicles in general with another paired passenger car. So we call this a source vehicle in front of the truck. And so in the case of this example, we actually have a Waymo car driving really far out in the range we're going to be labeling and data collecting as the source self-driving vehicle. And this allows us to actually label and synchronize these logs so that when we label this vehicle, we have a ground truth for exactly where that labeled vehicle was relative to the truck, the better part of a kilometer away. And that sort of transitive labeling allows us to turn an incredibly ill-defined and over-constrained labeling problem into one that is actually very similar to the sorts of labeling that we do day to day in up close and lidar range, where you have perfect localization accuracy and you're labeling a more traditional 2D or 3D image. And so that's an incredibly valuable and powerful addition to the suite. And so in the end, what we end up being able to do is create these like really robust data sets that go all the way out to this full range of that we're interested in, and we can really define these problems in a way that can map right back to our training systems in a way that leverages the existing infrastructure and gives us the information that we need. And this becomes really critical to overall operation. And so we put all this together, and we are now operating at a pretty large scale daily in both Arizona and Texas. And in Texas, we have a custom-built transfer hub facility in the Dallas area that is like designed from the ground up to be our first driverless transfer hub for operating an autonomous trucking operation out of Dallas. We also use it as our main operating facility out of Dallas. And we are driving daily now between these cities as well as many other routes and experiencing the full diversity of the situations that the world might throw at us. Some of this is very rural roads such as this one. Other times it's more complicated and interesting scenarios where you start to get into complex merges. As you get closer to cities, you get into dense traffic, construction zones, overpasses. You have to be able to react to situations like vehicles stopped on shoulder, where by law you have to transition over, stalled vehicles, aggressive drivers, traffic in this case as you're entering the Dallas metropolitan area, complicated dense merges, and then at all times maintain both the safety bar and the reliability that allows you to release this as a fully driverless system. And this is progressing incredibly well. It's both leveraging and benefiting all of the investment and scaling on the car program. And over the next couple of years, we will be operating fully driverlessly in Texas, with Dallas to Houston being our first route. So thank you very much. It's been a pleasure to share a little bit about the trucking challenges and the unique sorts of stresses that puts on the data and training problem for our ML system. And it's been a pleasure to join the conference. Thank you.